Hi, in this video we're going to be having another look at the Feeltech FY3224S 24MHz signal generator. So in my previous video we did an unboxing, had a quick look at the operation of this device, and then also did a teardown. And you'll recall that when we had a look at the leakage current from these output BNC connectors, we saw quite a high leakage current on this particular device of around 1 milliamp due to the switching power supply that's in here. And it happened to have quite a high value of EMI suppression capacity, which was leading to this high leakage current. On the EV blog forum, there's various reports of anywhere between 50 microamps and about 200 microamps. So it may be that mine was a bad one, or that they just accidentally fitted the wrong part in this device, but I'm sure there's a lot of users that haven't been on the EV blog forum that have one of these devices or that have even tested it. So there were quite a few questions raised. Why is this a problem? Obviously in my case this is an extreme case of 1 milliamp. This could easily fry your microcontroller or whatever you've got connected to the device. So it's something that I want to rectify on here. And ideally I'd like this device completely floating unless I purposely tie it to mains ground. So what I'd like to do is replace this switch mode power supply with a fully linear power supply. That is an EI core transformer or a toroidal transformer that provides complete isolation. And also this USB interface doesn't have any form of isolation, so as soon as you plug this into the computer, if your computer's earth, then the device is connected to mains earth. So I'd also going to have a look at isolating the USB interface. So the first thing that we need to do before we can specify a linear power supply for this is have a look at how much current it's drawing. So at the moment I've put a couple of 50 ohm terminators on the output jacks, and what we're going to do is put the clamp meter on the supply cables from the power supply and see how much current this device is using. So to measure the current being drawn by the signal generator, we're going to be using the Benning CM2 clamp meter. This has a DC current range which can use the clamp. It's probably not going to be quite as accurate as using the Fluke 87, but we'll be able to get a rough reading without having to cut any wires and connect the multimeter in series. And then when we design our linear power supply, we'll just add in a bit of extra headroom. So first of all, we'll measure the 5 volt supply, which is supplying the logic on the board. And that's this wire here, and that's drawing about 200 and 260 milliamps, something like that. It is going to be slightly skewed by the magnetic field of some of the other devices in the vicinity. That's a downside to using a clamp meter for reading DC, because it uses a Hall effect sensor which can be affected by external magnetic fields. But I'll just scribble down that reading. And then we'll have a look at the 12 volt supply. So that looks like that's this wire here. And here we're reading about 80 milliamps. And the minus 12 volt supply should be something of a similar magnitude. Let's see. Yeah, and we're reading about 90 milliamps. So we'll call it 100 milliamps for the plus and minus 12 volt supplies. So now we have those details, we can have a look at selecting a suitable transformer. So now we know the current requirements for each of the supply rails on the signal generator, we can design our linear power supply. So in the case of the 5 volt supply, we know that we want to be able to provide about 250 milliamps. So here's our traditional linear power supply circuit. So we've got a transformer on the left, a full bridge rectifier, a filter capacitor, and then we've got our regulator circuitry. And in this case I've selected a 6 volt AC RMS transformer. So I happen to have one of these from the Variac project. So it's just a little 6 volt amp model. And in this particular case, this transformer is specified as 6 volt AC RMS at full load. Some transformers you may have this voltage specified at other loads, so you need to make sure that you select a suitable transformer. And we get this AC waveform from our transformer, and then once it's full bridge rectified, we don't see the negative portion of the waveform. It gets reflected back up. So we see this half sine wave, and it actually has a period of half this waveform. So in the UK we've got a 50 Hz AC supply given as a period of 20 milliseconds, and once you passed it through a full bridge rectifier, the period of each of these is only 10 milliseconds. So what we want to do is work out what value of capacitor here will maintain a voltage at this point here that's always greater than the 5 volts plus the dropout voltage of the regulator. So the smoothing capacitor ends up providing the waveform here that I've drawn in red, which you might be able to see. So it follows the waveform on the positive side here, but as you draw current from the power supply, that capacitor starts to discharge. Obviously the AC waveform drops off here, so we're using the capacitor to provide charge to the circuit, and then once you get this rising edge here again, it starts charging up again. So what we want to do is choose a capacitor that stops this voltage here ever being less than 5 volts plus whatever your dropout voltage is on your regulator. So the regulator that I've selected is one made by ST Microelectronics, so the LF50ABP, and this has quite a low dropout voltage at 400 millivolts. I think if we chose a 7805 or something like that, that one may have a dropout voltage that's too much for this particular transformer being used. So at full current on this regulator, the dropout voltage is 400 millivolts. So this voltage at this point here always has to be greater than 5.4 volts. And we've already said our rectified AC voltage here is 8.484 volts. And then after the bridge rectifier, that's going to drop to about 7 volts because we've got the voltage drop of these diodes here, and there's always two conducting at one time. And then we've got our capacitor equation here, so it's traditionally written I equals C dV by dt, but we can rearrange that to give us capacitance, so C equals I dt by dV. And if we fill in some numbers here, so our current is 250 milliamps, the period dt is 10 milliseconds, and then the delta V is this voltage here minus the minimum voltage here, which gives us a value of about 1.48 millifarads or 1480 microfarads. So I think in this circuit we're going to use two 1000 microfarad capacitors in parallel. And we can do exactly the same analysis for the 12 volt supply. So in this case we need a plus and minus 12 volt supply, which we can do with a center tap transformer or a transformer with two secondary windings. And again, I've got another one of those same style transformers, a little 6 volt amp model, two 15 volt windings here. These are left over from another project, so I thought I'd use them. They're quite compact. And what we've got is the two 15 volt windings with the center tap connected to our chassis 0 volts, so the 0 volt rail on the signal generator. We've got a full bridge rectifier, and in this particular configuration that gives us a positive voltage at this point with respect to this 0 volt and a negative voltage with respect to the 0 volt line just here. So if we follow through the same analysis, so we've got 15 volts RMS times 1.414 minus just one diode drop in this case, that gives us 20.51 volts at this point here. We're just going to use a 7812 and a 7912 regulator here. And those have a dropout voltage that's quite high at 2 volts, so that's why it wasn't really suitable for the 5 volt supply. Which means that the delta V is about 6.5 volts, and that's the worst case. Obviously we don't really want that much ripple voltage, we want to give us quite a bit of headroom, but if we put all the numbers in the equation again, that tells us that we need a capacitor of at least 230 microfarads for each of these. Obviously if we have bigger capacitors, the dips here get smaller and smaller, so that you don't see very much ripple voltage at all. And then the final thing that we need to consider is the power dissipation in the regulators. So obviously we could have derived our 5 volt supply from this 15 volt rail, but there's a good chance that that will provide quite a lot of dissipation in the voltage regulator. So we can do a bit of analysis on the power dissipation. So simply our power equation is P equals IV, and for the 5 volt rail we've got 250 milliamps, and the voltage that we're dropping in the regulator is 7.084 volts minus the 5 volts, which gives us about half a watt of dissipation. And for the 12 volt rails, we've got quite a bit more because we're dropping that 20 volt rail down to 12 volts. So at 150 milliamps, that gives us about 1.25 watts. So in total, our power dissipation in the regulators is about 3 watts. So obviously that gives an indication why linear power supplies aren't necessarily the best, because we're going to be creating a bit of heat inside the case. So to work out the heatsink that we want, we can just work out here. Basically, I'm willing to accept at least 10 degrees temperature rise between the heatsink and air. So for 3 watts, that means we need a heatsink with a thermal resistivity of about 3.3 degrees C per watt. And another thing you could do to get rid of a bit of the losses here, if you did want to use just a dual 15 volt transformer, you could use a DC to DC converter to drop this 15 volt rail down to 5 volts, or if you want a slightly cleaner supply, you could drop it down to something like 7.5 volts or 7 volts and then use a linear regulator to get your 5 volts. But certainly on eBay there's quite a few modules. You don't need to build all of this up. You can buy a little module on eBay that accepts the input from a transformer and will give you plus or minus 12 volts. Plus or minus 15 volts is a bit more common, but there's definitely modules out there that have adjustable regulators here, which would allow you to get these two values here. And you'll also notice we've got a couple of capacitors here. These ones are the ones that are doing all the work, so they're smoothing out that rectified sine wave, ready for the LDO. These just really need to be able to cope with any spikes of current that may be drawn by the signal generator. So we can just select some fairly arbitrary value capacitors for this, and obviously check with the oscilloscope when we've got it powered up that we're not seeing any nasty waveforms. So I think what we're going to do is mount the transformers on the left hand side here, leaving as much space in this area as possible. It looks like we might just have to mount them slightly offset, so in this kind of arrangement here. Obviously we're going to redo all of the wiring for the mains. This is really quite flimsy, and I saw on some people's units on the forum, these wires are pretty close to this board here, and if something happened to one of these and it came off, there's a good chance you could end up with mains on the front PCB. So obviously this is going to all be made a little bit safer. And then I've cut out some Vero board, so we should be able to mount this in the middle here with the TO220 packages on the left hand side for the regulators, and then all the other components towards this side, and then we'll have a connector to supply the power to the PCB. And then there should be enough room here for the isolator board for the USB connector. So I'll just start building up this board here with the voltage regulators and linear power supply circuitry. So here we have our regulator board, which I've just finished soldering up. So at the back here we've got the 5 volt regulator, the minus 12 volt regulator, so 7912, and the 7812 here. We've got the inputs here, which are going to come from the transformer. We've got our two 1000 microfarad capacitors for the 5 volt rail, and I've put a 1000 mic capacitor for after the regulator. We've got our two capacitors here. I've used the same 1000 microfarad capacitors for each of these, and then the outputs on those have got 470 mic capacitors. And then we've got our output here to the signal generator PCB. And then on the bottom we've just got some of the routing, and I've put some 100 nanofarad capacitors on each of the supplies to help stop these regulators oscillating. And these regulators are all mounted in line. So I've got a heatsink here which has our requirement for better than 3.3 degrees C per watt. And these regulators are all in the plastic packages, so we don't need any sill pads. And these will just attach to the heatsink with some clips. And then what I've done is I've cut some acrylic on the laser cutter, and the idea is that we'll be able to screw this acrylic to the plastic base, and then we'll be able to mount the transformers directly to the acrylic rather than the case. Because this is a double insulated product, I don't really want to cut the back panel to fit a 3-pole connector for the mains. So if we had screwed these transformers just through the case and had some metal screws going through the case. In the event of a fault, it's possible that those screws could become live, so what you'd have to do is earth these transformer chassis. By mounting them to the acrylic and then screwing the acrylic to the case, we maintain the double insulation. So I think I'm going to mount these kind of in this formation on this side. Then we're going to have the regulator board somewhere around here, so that'll fit kind of like that. And there's a cutout here, that's for our USB connector at the back here. And then there's a little bit of space here, and what we're going to do is we're also going to design a little isolator for this USB interface here. I'll probably do that in the next video when we look at the PC software. The aim of this video is just to get all this up and running, and then we're going to have a look at the waveforms from the signal generator, just so some of you can see how it behaves at high frequencies and see if it's an item that you want to buy. So what I'm going to do is I'm now going to mount the heatsink to the acrylic, and then also clip the regulators to the heatsink, mount the transformers, and then we'll have a look at wiring this all up. Right, so you can see how this is starting to come together now. Unfortunately, when I was using the self-tapping screws on this heatsink, it went on a little bit wonky, and rather than trying to re-tap the holes, I decided to just stick with it. So this is slightly on the wonk, but never mind. So we've got the transformers on the left here. These are bolted to this piece of acrylic. Obviously we've got the power supply board here, which is also bolted to the acrylic. And then we've got the regulators clipped to the heatsink, and this is all really nice and rigid, so it shouldn't be going anywhere. And what's left to do now is to wire all of this up. So on the actual signal generator itself, all of this mains wiring was pretty flimsy, crappy stuff really. So what we're going to do is we're going to tidy this up quite a lot. It looks like the switch is glued in. I would have liked to have replaced the switch with something slightly nicer. It looks a little bit cheap. But we'll just desolder these wires. Obviously we don't need the old power supply board anymore. We'll take the wires off the figure of 8 connector, and then we'll put some nice probably 1mm squared cable on there with a heat shrink and everything, and make it all a lot tidier. And then yeah, we just need to make up a few cables just for these Molex connectors to go onto the 15V supply and the 5V supply directly from the transformer. And then we just need to make a cable to go from here to the front panel PCB. Right, so I've connected up the transformers to the regulator board, and I was just about to mount this back in the case and start wiring up the back panel connector, but I thought I'd give it a quick test on the Variac. So what I've found is the 5V rail is working absolutely fine, and the 12V rail is working absolutely fine, but I'm having a bit of trouble with the negative 12V rail. So what I'm seeing is that it's just not regulating properly. And I've obviously traced out the circuit just to make sure I haven't made any mistakes, but I can't find anything wrong with my board. It doesn't seem to be oscillating or anything like that. So we've got the oscilloscope connected up here. We've got channels 3 and 4, that's pink and dark blue, connected to the output from the 15V transformer. We've got channel 2, that's the light blue, connected to the output from the bridge rectifier. And it's also got the capacitors on there as well, so we'll see a smooth DC voltage. And then we've got channel 1 connected to the output of the minus 12V regulator. So I started increasing the Variac, and you can see that we've got the AC waveform coming from the transformer, and you can see that the output from the regulator is obviously following close to the peak, but it's not regulating yet, so it's just at minus 3.6V. And we increase the voltage, and you can see there it's all of a sudden started clamping at minus 11.2V. On the Rigol this voltage is slightly off. I think it needs just a little calibration doing. It is closer to 12V, minus 12V than this. But you can see it's quite happily sitting there at minus 11.2V. And then we start increasing the Variac further, so we're getting closer to mains voltage now, we're at 190V. And you'll see that this voltage is starting to increase now. And the regulator just isn't regulating at all at this point. So here we are at 240V, and it's gone way off. It's now at minus 17.2V. So obviously it's slightly odd behaviour. It was definitely regulating for some period of time, and then you can see it stops regulating when it's just getting above about 20V, I think it was. So I started having a look at the datasheet, and I couldn't really find anything which would explain this kind of behaviour. It's rated for up to minus 35 volts input. We're not getting close to that, so I really started to get a little bit puzzled. And then what I did is I just grabbed a fan. It was just on the desk, and I applied that to that rail, and all of a sudden that voltage rail drops right back down to minus 11.2 volts, and it's regulating properly. So it looks like this regulator wants a minimum load, and I've not really seen this from a 7912 or 7812, any of those style regulators before. But I had a look in the datasheet, and all of the specifications seem to be in the range of 5 milliamps to 1 amp. So there's no specifications which say anything about the load regulation or anything like that below 5 milliamps. So it looks like on this particular regulator from ST Microelectronics, we need a 5 milliamp minimum load. So although the signal generator is probably going to draw that kind of current from the supply rail, I'm not really happy with this supply going out of regulation if for some reason it decided not to draw any current from that rail. So I think what we're just going to do is add some power LEDs to this board. We'll just set the current to 5 milliamps. And that should be fine. So I'm just going to solder some LEDs on here, and then we'll just double check that that's worked. Right, so I've just soldered some yellow LEDs onto the PCB here. The current on these is about 6 milliamps. That was the best value resistor that I had. I've also added one to the 5 volt rail, although it's definitely not needed on that regulator. That one's specified into no load. So now if we increase the voltage on the variac up to mains voltage, so we're at 240 volts now, you can see that's happily regulating. It says on the scope at minus 11.2. It's again closer to 12 volts with the multimeter. So that was a slightly annoying little bug, a fault that took about half an hour to diagnose. But the clue was that it was regulating for a period of time, and then it fell out of regulation. If it had have just not regulated at all, I would have been suspecting a faulty regulator, and I probably would have ended up replacing it and finding the same fault, and then being a little bit more suspicious of my circuit or something like that. But the fact that it was regulating for a while indicated that it definitely was connected up right. There was just some issue either with oscillation or a minimum load. So that seems to be happy now, so we'll screw this all back together, and then I'll just connect up the mains wires to the front panel switch and the figure of 8 connector at the back, and then we can give the signal generator a test. Right, so here we have the unit partially assembled again, ready for test. So we've got obviously the regulator board in the middle. We've got the transformers on the side here, and they're bolted to the acrylic sheet. I've got the front panel switch wired up, soldered, and then we've got some heat shrink tubing with the adhesive inside. And then I've added a fuse to the rear panel. So the switch mode power supply had a little glass fuse in it, but obviously we've got rid of that. So now I've put in a little 20mm fuse holder to the back panel, so that I just drilled a hole in the back panel there, and that's got a 2 amp anti-surge fuse in there, and then all of this has got heat shrink tubing on as well. So we should be ready to give this a test. I've not put the USB interface board back in, because in the next video we're going to design a little isolator for that, so that this device is completely floating unless you actually connect one of the BNC shields to ground. So I'll just grab a mains lead, and we'll also grab a multimeter and just test the output voltages one last time before we plug it in and see if the device works. And before we power up the signal generator for the first time, we'll just do a quick safety test. So we're going to do an isolation test between the mains plug and any of these points that you can touch at the front, just to make sure that we've got a good isolation. So here we've got the Fluke 1654B multifunction tester set to insulation test at 500 volts. So if we hold this button, we can do the test. And you can see that's given us a reading greater than 500 megohms. And we'll just repeat the test here on one of the output jacks. Obviously we've got the other end connected across the mains plug, so live and neutral here, the clip's connected across. So we'll do one more test. And there we go, so we've got the test voltage there, it's 521 volts. and we're still reading greater than 500 megohms. So that means that we can now plug in this device and be sure that we're not going to get an electric shock or anything off these front panel connectors. Right, so I've connected the main supply at the back, and one thing that's worth mentioning is that this has a figure of 8 connector on the back, so that's an unpolarised connector, so you can connect the plug into the socket either way round. So I've only got one fuse in here, and the switch on this unit is a single pole switch, so we can only switch one of those lines. And in this case it doesn't really matter that we're not switching or fusing both poles. What we're trying to do with the fuse is just protect against overload, so obviously if there's an overload situation the fuse will blow, and since there's no other path after these transformers the device will still be protected. Similarly with the front panel switch, we just want a power switch, we're not trying to isolate power to this device, so it doesn't really matter if it ends up on the live or neutral. And I also just want to get a piece of acrylic cut just to glue on top of the transformers here, because these terminals on the top of the transformers are obviously live when it's turned on. There's a little solder joint on the top of the transformer. So I'll just turn on the front panel switch, and you can see we've got the LEDs on, so we'll just quickly test all the voltages and then we can connect up the signal generator front panel. So I've got a ground connection on the top of the whole of the PCB, and there we've got our 5 volts. The next one should be the -12, and then finally a 12 volt on the end connection. So that all looks correct. I'll just double check my wiring to the front panel onto this Molex connector, and then we'll try powering it up. Right, so here we go, the moment of truth. Let's turn it on and see what happens. And there we go, that seems to be working properly. We can just test the voltage just to do the same test that we originally did when it had the switch mode power supply. So on DC, we're getting nothing there. What about on AC? We're getting a little bit of voltage there. It's basically nothing. We can just measure the current. It should have no current behind this, so I'll just plug this in. And here we go, we're on the microamp range on AC. And there we go, yeah, bugger all, it doesn't read anything at all. It's no different to having the probe disconnected. So we can now see that this is completely floating. And what we'll do now is we'll just have a look at the waveforms. Quite a few people asked what the waveforms look like, particularly at high frequency. So we'll connect it up to the oscilloscope and see what it looks like. Right, so let's have a slightly more in-depth look at some of the waveforms, so particularly at higher frequencies, something which was requested by quite a few people in the comments. So that's something I didn't look at in the previous video, and also after shooting the previous video I suddenly realised what all of those resistors and analog switches were doing on the back of the PCB. So they're creating an R2R ladder instead of using a dedicated DAC chip. Which means that the FPGA doesn't have to create an SPI or I2C peripheral in VHDL or Verilog. You can just output a digital representation of the number of the analog voltage that you want to represent. And you can read all about R2R ladders, but they're quite an easy way of creating a DAC where you can just output directly the digital number that you want to represent. Obviously the quality of the DAC depends on how well those resistors are matched. I doubt that they're using highly precision resistors in this device, so what we may see when we zoom in on some of the waveforms is, particularly at the zero crossing waveform and halfway up, you might see a little bit of what looks like crossover distortion or something like that, and that's basically where the most significant bit, or maybe the second to most significant bit, rolls over, which means that previously, for example, you had 7 resistors in series creating the analog voltage, and then you switch over to the 8th bit where you've only got 1 resistor there, and obviously it relies on those resistors being matched to have no distortion. So obviously if they're using only 1% resistors or something like that, we're likely to see a few glitches at this point and halfway up. So let's increase the frequency and see how the waveforms look. So we're at 1 kHz at the moment. I'll switch over to changing in 100 kilohertz steps so that we don't take forever doing this. So here we have 100 kilohertz, that doesn't look too bad at all. Let's increase it further. 500 kilohertz, and here actually you can see exactly what I mean. So there's some slight little glitches at the zero crossing point and halfway along. Let's take it further. So we've got 1 megahertz here, that's not looking too bad. You've obviously still got these glitches here, and I think these are going to be persistent the whole way. So that's 2 megahertz, 3, 4, 5, 6, 7, 8, 9 and 10. So overall that's still not looking too bad. 15 megahertz, 20, and there's 24. So we're just seeing a slight bit of distortion here. It's not quite looking as sinusoidal, and also you may have noticed that the amplitude just decreased slightly at the end there. And all of those previous measurements were taken with an amplitude of 5 volts. Let's increase this up. So here's the full output voltage, 20 volts peak to peak. And we'll start changing the frequency again. So we're at 1 megahertz here. That's 5 megahertz. 10 megahertz. Let's change the time base slightly. And I think we're just starting to see a little bit of a change to the sine wave here. And we're definitely seeing a decrease in amplitude. So it did have a pair of op amps for the output stage, and it looks like maybe the gain bandwidth of those is starting to be affected here. And yeah, at 24 megahertz, it's not looking far off a triangle wave. So it looks at about 7 or 8 megahertz is where we're starting to lose the sinusoidal signal at the full amplitude that the signal generator can produce. If we take it right down to very small voltages, we can have a quick look to see what they look like. So that's 10 megahertz with a 100 millivolt peak to peak signal. It's starting to look a little bit noisy. What does it look like with a single shot? Yeah, so you're seeing a little bit more distortion of the waveform here. If we keep increasing this up, we're losing quite a lot of the sine wave, waveform. So I hope that gives a bit of an idea as to how it behaves with some of the higher frequency waveforms. If anyone has any specific requests, I'm going to do one more video on this, talking about the USB interface and also arbitrary waveforms, obviously, so I can include a few more captures there. And I did also just want to say thank you to my Patreon supporters. I don't really expect people to donate, but if they do want to, then it will go towards either lab equipment or components for future projects. But a big thank you to those that are Patreon supporters. Any donations are gratefully received. So I hope some of you found this video useful. Obviously you don't have to go to the complete extent of replacing the power supply for a linear power supply. Another thing you can do is obviously change that capacitor that's on the switch mode power supply for a lower value to reduce the leakage. Or you could change the connector on the back of the signal generator for a 3-pole connector that has an earth. And you could connect these BNCs directly to mains earth through the 0-volt connection on the PCB. Obviously that means that then everything that you connect to this is going to be mains earth referenced, and I wanted the ability to float this device and tie it to ground, obviously, if you want to. And we tested the insulation resistance with the insulation tester, and this can be used with these devices floated up to 500 volts. Obviously, you don't really want to be doing that unless you know what you're doing, but it showed that the insulation was good enough that you could have this device running, at the top end of a circuit, driving some transistors or something like that. So in the next video, what we're going to do is we're going to create an isolated USB interface so that the device remains completely isolated even if you've got it plugged into your computer for downloading arbitrary waveforms. And if anyone has any further requests for any measurements that they'd like to see, then obviously include them in the comments below. I will write up all of this on my website, so don't forget to visit the website. But I do think this is quite a good value signal generator. With the modifications, obviously it's becoming a little bit more expensive, but it does seem quite well featured and it's nice and easy to use and everything. So I'm quite happy with this. I would recommend it to anyone who wants a signal generator for their bench but doesn't have the big bucks to buy a nice Agilent signal generator or anything like that. This obviously isn't as good, but it does the job, particularly at the kind of frequencies that hobbyists are likely to want to use something like this for. So I hope you enjoyed this video. Don't forget to give a thumbs up if you did, give it a thumbs down if you didn't like it, subscribe if you haven't already, and thanks for watching.